Okay, I'm hoping I'm not in the wrong class. It's only around 50 students out of a possible 90. Well, but in any case, I should not keep the students here waiting. And so we probably have to start in any case. Last week, we have already started on the second topic in the lecture notes set number 3. And it is a continuation of the chapter 16, which is related to the wave motion. The idea of the chapter 15 is the oscillatory motion. And in particular, we will be looking at the simplest form of the particle oscillation, and that is the simple harmonic motion. So it is, of course, related to the waves, because in the case of the waves, you have the medium that is oscillating, that have the particles oscillating, and it is this particle oscillations that brings the movement of the energy from one place to the other. During the process of the energy transmission, you have the particles that are moving back and forth. So they are actually performing a simple harmonic motion. And here we would take a look at the reason why we have the simple harmonic motion. And as we start the lesson, we introduce the simplest case of the simple harmonic motion by looking at a particular example of a spring and mass system. So what is special about this particular system? In the spring and mass system, well, let us forget about the case where you hang the particle from the spring and have the spring extended to start with. Let us have the even simpler case. You put the spring and the particle on a horizontal surface, and there is no friction. So it is basically an isolated system. It would remain at rest unless you have some external force that would kickstart the motion for the system. What happens here is initially you would have to, for example, give a initial position for the particle. If you keep the particle at the equilibrium position, x equals to 0, the system will not oscillate. It will oscillate only when you start by, say extending it to a location where x is larger than 0. When you extend the spring such that it is beyond the equilibrium position, it would have a spring force. The spring force is in the opposite sense as the particle displacement. So you could see that the particle is displaced from the equilibrium point by x. At the same time, the spring would provide a restoring force. Such that it points in the negative x direction. Of course, the restoring force, if you are not providing the external force to counterbalance the spring force, the restoring force would help to accelerate the particle back to the equilibrium point. So if there is only the spring force, that is present, it would try to bring the particle back to the equilibrium point. So the acceleration, which is due to the spring force, it is pointing in the negative x direction. And that is why it is called a restoring force. At the beginning, you have the particle displaced in the positive x direction, and the restoring force is in the negative x direction. At the beginning, the particle may be at rest, but when you release it, due to the acceleration, it will start to gain velocity as well as, of course, momentum and kinetic energy. Okay, later, the particle would come back to the equilibrium point where there is no further extension of the spring. So that is the situation in B. Particle comes back, no further spring force, no further external force on the particle. But because of the inertia, the particle actually keeps moving. It is easy to understand by even the common sense. The particle initially is at rest when it is in the situation A. But when the spring is released, it would accelerate, the particle will accelerate. And when it comes back to the equilibrium point x equal to 0, it has certain speed. And because of inertia, the particle would keep on moving and overshoot the equilibrium position. Finally, it would move to the negative x direction, where the spring would be compressed, and it would provide a force that is once again opposite to the direction of the particle displacement. And so it is once again a restoring force. It is restoring because it always tries to bring the particle back to equilibrium point. It is restoring because it is trying to push the particle back to the equilibrium point. The force is pointing in the opposite sense as the particle displacement. So this is just one half of the cycle. Of course, when the particle is stopped due to the continuous deceleration, it would repeat the cycle, but in the opposite direction. And then it would go through the cycle once again. So that is the physical picture. In terms of the mathematics, that is what we would need. Basically, the spring would provide the net force to the whole system. And the spring force is equal to minus kx. That is what we have just discussed. It is the restoring force. So it is in the opposite sense as the particle displacement. So you have the negative sign, minus sign at the beginning, and the magnitude is k times x. And of course, this restoring force would be responsible for the particle acceleration. So it is equal to m times a. Now, we have basically established a general situation. The general situation is like this. Whenever you have a motion, if the motion is in the form such that the acceleration is proportional to minus x. If the acceleration is proportional to x in the opposite direction with the x, and if you could represent it by something like this, a is equal to minus omega square x. Why we use omega square? When you have a number that is real, say if omega is real and you have it squared, it is always positive. So you are having a positive number for omega square. And if a is equal to minus omega square x, then basically it would be performing an simple harmonic motion. So that is the general case where we would decide whether the motion is a simple harmonic motion or not. If you could write an equation such that the acceleration is equal to minus x times a positive number, then it is a simple harmonic motion. The solution for such a simple harmonic motion, it is basically a sine or a cosine function. Let us, at the beginning, say it is a cosine function. It could become a sine function if you have the phase angle equals to pi over 2 or minus pi over 2. So it is not a big issue. But let us try at least at the beginning, say it is a cosine function. So you could see why omega is important, because omega goes now into the cosine function. And from the study of the waves, we know that omega, it is the angular frequency, and it is related to the frequency by the equation omega equals to 2 pi f. So if you have the equation at the top, a equals to minus omega square x, then the general solution for x, it would be equal to a times cosine omega t plus phi. Thus, omega is equal to, well, it is not a definition. It is the case that in the spring and mass system, omega, it is equal to k over m in the, well, square root k over m in the spring mass system. In other situations, omega would be some other combinations. As you will see later for the simple pendulum, omega is not k over m. But as long as you have a equals to minus something times x, this something would be equal to omega squared. And here, the something happens to be k over m. That is how we understand this. In the case of the spring mass system, the coefficient happens to be k over m. And we could regard it to be the omega square. And so the omega square in the case of a spring and mass system is k over m. So here you could see the k over m could substitute into the omega square in this case. And for the general solution, in the case of the equation at the top, here, this one, the general solution, it is this one. X equal to a cosine omega t plus phi. The exact values of a and phi, they have to be decided case by case. Just think about the spring and mass system, how much the particle oscillates. The amplitude depends on situation. And what is the starting situation also depends on the particular case. So we will see in the later 2 slides later, the 2 different situations. But general solution, once again, the one at here. For students who learn about calculus, they would recognize that velocity for any motion, it is equal to dx over dt. And the differentiation of a cosine function would lead to a minus sine function. So this would be the solution for the velocity. As you will see, the amplitude of the velocity, it is equal to omega times a. So they are actually related to the amplitude of the displacement. Now, forget about the negative sign because we are just talking about the size of the velocity. It could be positive or it could be negative, but the size is omega times a. And then acceleration is the differentiation of velocity with respect to time. So you would have omega squared times a times cosine omega t plus phi. To understand why we obtain these two equations for v and a, you have to go to the AMA lesson, I'm afraid. But here we provide you with the solution and we highlight at here the important facts, namely the amplitude of the velocity and the amplitude of the acceleration are actually related to the amplitude of the particle displacement. That is important message at here. The fluctuation of the velocity, acceleration, and the displacement, they are always sine and cosine function. And of course, given that they are sine and cosine with respect to t, so they would have some phase relation, which we would not go through in details at here. But we will see actually in the next two slides. So in the last lesson, we have gone through two examples of simple harmonic motion. In particular, the two examples of the simple harmonic motion in the spring and mass system. The first case, it is the spring that is displaced from the equilibrium point at the beginning and then released from rest. So if the general solution is xt equals to a cosine omega t plus phi, when you are given the initial conditions like this, that means when t is 0, x is equal to a, because it is displaced from the equilibrium position at the beginning. So t equals to 0, x is equal to a, and at the beginning, it is released from rest, so v is equal to 0. With such conditions, you will see that phi, the phase angle, has to be 0. So that is why you have the equation xt equals to a cosine omega t. We start with the general solution and then try to fit in the numbers by putting in specific conditions. That is the idea. Velocity follows. Once you decide the phi and a, velocity becomes omega a sine omega t, and acceleration becomes minus omega square a cosine omega t. So that is how we work it out. When you draw the diagrams, these are the displacement, velocity, and the acceleration diagrams as a function of time. They are like shifting from one another by pi over 2. So that when you have the, say, the x over t, it starts from the maximum a and then perform a cosine function. In the case of a velocity versus time graph, it is like shifting the velocity versus time graph by 90 degrees backward. So it starts from 0 and then drops and then goes up like that. They have a phase relation with one another. Basically, the phase difference between the particle displacement and velocity is 90 degrees or pi/2 radian. Similarly, between the velocity and the acceleration, it is like shifting the whole graph by 90 degrees or pi/2 radian. So that is how we understand these graphs. And that is the situation for the first example of spring mass system. Particle extended to the maximum and released from rest. In the second case, you have the particle that is given a kick at the beginning, and it starts with an initial velocity, vi, for example. So it starts from t equals to 0, x is equal to 0, and v is equal to vi. Let us say it is a positive value. It is a positive velocity. So how do we work it out? Xt is equal to a cosine omega t plus phi. And then Vt, if you go back to the equation on page 24, it is equal to minus omega a sine omega t plus phi. In order to fit in a positive value, for the velocity at t equals to 0, you have to put in phi equals to minus pi/2. If it is a plus phi/2, it will start with a negative velocity. So that is why here we have to fit in a minus pi/2. And the velocity is equal to vi. In fact, if you are keen to work out what is the value of a, you will see that vi is the maximum velocity, which is equal to omega times a. So a would actually be equal to vi divided by omega if you are really keen to work it out. That is how we see the picture. In any case, the particle displacement, it is equal to a cosine omega t minus pi/2, and it becomes the sine omega t. Velocity is omega a cosine omega t, and acceleration goes on in a similar case. So that is the two examples to show you how to decide the value of phi and the value of a. It depends really the specific situation. Angular frequency and the period of oscillation, we have assumed that that is something related to the wave. So we have make use of the fact that omega is equal to 2 pi f. So the f is the actual frequency and omega is the angular frequency. Of course, the actual frequency is related to the period of the oscillation. Okay, now I'm coming back to the point of discussing the value of minus pi/2 as asked by some of your classmates. You could have plus pi/2 or minus pi/2, but if it is initial velocity that is equal to vi. If you try to fit in a plus pi over 2, then it would give you a negative vi. So that is why we try to fit in a minus pi over 2 in order to jiggle around with the whole scenario. Okay, so these are all related to the period and the frequency of the system. So for the case of the mass and spring system, as we have discussed, the acceleration, it is equal to minus k over m times x for the spring and mass system. And because for the simple harmonic motion in general, for simple harmonic motion, A is equal to minus omega square x. Therefore, in the specific case of the spring and mass system, omega square is equal to k over m for spring mass system. And therefore, the period of the oscillation, it is equal to 2 pi times f. Let me see. Sorry. The omega is equal to k over m. So f, it is equal to omega over 2 pi. So that is equal to 1 over 2 pi square root k over m. And t, it is 1 over f. So that is just the inverse of the term that we have just seen at here. Your classmate is asking, so omega is equal to 1 over 2 pi over t is for the wave function. Once again, for simple harmonic motion, here it is the equation. But now we are talking about spring mass system. So for the spring mass system, what is omega? For the spring mass system, omega is equal to square root k over m. It is for spring mass system. For the spring mass system, omega is equal to k over m. And in all the simple harmonic motion, in general, for the simple harmonic motion, omega, it is equal to 2 pi f. And the period, it is 1 over f. That is something we could understand when we refer to an oscillating system. Frequency and the period, they are just the reciprocal of one another. I hope I may have addressed your question. So please be very careful on the situation. We have been discussing at here simple harmonic motion. For simple harmonic motion, please remember this one. A is equal to minus omega square x. Omega, it is a term that we have to decide according to the specific scenario. For the specific scenario, which is a spring mass system, we could see that omega becomes square root k over m. And that is why we could say for the spring mass system, omega is equal to square root k over m. Once we know the omega, we could determine the frequency by the equation omega equals to 2 pi f. And once we know the frequency, we could determine the period by t equals to 1 over f. So that is how we work out the situation. Now, let's take a look at an example. And here, you will have a block connected to a spring, and the spring constant is 5 Newton per meter. It is oscillating on a smooth horizontal surface. Displacement is 5 cm from the equilibrium and release from rest. So you're asked to determine in part A the period of the oscillation. For the spring and mass system, once again, for the spring and mass system, you could write down the equation of motion, ma equals to minus kx. So a is equal to minus k over m times x, which have the characteristic of the simple harmonic motion. Because in the simple harmonic motion, we are always looking for the equation form a acceleration equals to minus something. Let's call that something to be omega squared, and it is multiplied by x. So compare this one to this one. You could see that omega squared is equal to kx, k over m for the spring and mass system. So we could see omega, it is equal to square root k over m, as highlighted here. So the rest is just a substitution of the numbers. The unit here is radian per second. It is the angular frequency. So that is the unit of the angular frequency. Period of the oscillation, it is equal to 2 pi over omega. And so that is the time of one oscillation. Maximum velocity and the maximum acceleration can be decided by the amplitude of the velocity and the amplitude of the acceleration functions. So omega A and omega square A. Omega is decided in part A. Amplitude, it is 5 cm. So that is why you have the velocity and acceleration values at the maximum. That is decided by the equations. Now, we try to further understand the energy conversion during the oscillation process. The idea is that you are having the oscillation of the spring mass system on a frictionless surface. So all the energy is conserved, and it is basically an isolated system. Total mechanical energy should be constant. From time to time, you will have the particles that is oscillating, that is moving, so it has kinetic energy. And from time to time, the particles well, the spring would be extended. So there is elastic potential energy. Total energy of the system must be conserved. So the sum of the two must be a constant. What is the kinetic energy? At any location during the simple harmonic motion, it is equal to 1/2 mv squared. So we try to put in the numbers. Velocity, the equation is the one at the top, minus omega a sine omega t plus phi. So that is the equation for the kinetic energy. And what about the elastic potential energy? It is 1/2 kx squared. X is equal to a cosine omega t plus phi. So you put in here, and you could see that when you add them together, it naturally becomes 1/2 Ka squared. So it is a constant, which is something assuring, because we found that we are not actually doing any mistake. The total energy should be conserved. If you try to plot the variation of the energies as a function of time, that is the general behavior. When you plot the kinetic energy and the potential energy as a function of time, you will see that there is a constant interconversion between the two types of energies. When one goes up, the other one comes down, and vice versa. In all these diagrams, we assume that the particle starts from rest. So the kinetic energy is the maximum at the beginning. The elastic potential energy is at the maximum at the beginning. But even if you kick the system from the equilibrium position, from the equilibrium point, you will still obtain the same conservation of energy behavior. On the right-hand side, it tells you how the kinetic energy and the elastic potential energy varies with respect to the location from the equilibrium point. So they may be displaced from the equilibrium point, which is at 0. When the particle is at the equilibrium point, elastic potential energy should be 0. But you have a maximum kinetic energy. Similarly, at the extremes, the elastic potential energy would be maximum, but no motion exists, so kinetic energy is 0. They could be obtained basically, the two functions can be obtained basically from the equations above. And this would once again show you how the energy varies during the whole process of the simple harmonic motion. Starting from maximum extension, you will have the maximum potential energy. And it is basically a whole energy of the system. And when the particle comes to the equilibrium point, all the potential energy becomes kinetic energy. In all of them, the total energy is constant. You are just interchanging energy from one form into another. So if you really want to decide the energy or the velocity at a given location from the equilibrium point, this is how we could do it. The total energy is 1/2 Ka squared, and that is equal to 1/2 mv squared plus 1/2 kx squared. So you could readjust the terms and represent V, the velocity, as the subject of the formula. So it can be positive or the negative omega times square root a squared minus x squared. It could be positive or negative depending on whether the particle is moving in a positive x direction or into the negative x direction. So because you have the particles that is oscillating back and forth from time to time. So the velocity can be positive or negative, but at the same location from the equilibrium point, apparently at the same location from the equilibrium point, the magnitude of the velocity seems to be a constant. The amplitude of the velocity seems to be a constant. That is the idea. Okay, now we take a look at another example. Here we have an oscillation on a horizontal surface, which is once again a spring mass system. The particle is a 500-gram cart connected to a spring with a spring constant 20 Newton per meter. You're asked to decide what is the maximum speed in the part A if the amplitude of the motion is 3 cm. So the maximum energy of the whole system, if you go back to the page 32, page 31, if you go back to page 31, the total energy or the maximum energy possible in the system is 1/2 Ka squared. So largest velocity, largest speed can be obtained when it is all in the form of kinetic energy. That is why you have 1/2 Ka squared equals to 1/2 mv squared. And indeed, in this way, you decide what is the value of the maximum velocity. At the position 2 cm from the equilibrium point, the velocity could be determined by the equation at the last page. V equals to square root K over M A squared minus X squared. So that is how you decide the velocity. There are two possible values. As I've said, the particle could be moving to the positive x direction or coming back. So it moves in the negative x direction. So you could have positive sign or negative sign. And finally, you are asked to calculate what is the kinetic and the elastic potential energy of the system when the position of the cart is 2 cm. Once you have decided the velocity, you could determine the kinetic energy, and by subtracting the kinetic energy from the total energy, you could decide the elastic potential energy. So that should be the idea of working out this particular question. Okay. Right. At this point, I would like to go to the tutorial question, which should be available. Let me check. It should be available on the Learn at PolyU. So we go to tutorial 4, and let us take a look at question 2 of the tutorial 4. Which part you're talking about? If you want to decide the direction to be positive or negative, actually it's not necessary, because the velocity should be the size of a velocity, or the speed should be the same. And the kinetic energy does not depend on the direction. Okay, so at here you have a once again the spring and mass system, and it oscillates with an amplitude of 4 cm on a frictionless horizontal surface. You're asked to decide what is the total energy of the system, speed of the object when it is 1 cm from the equilibrium point, kinetic energy, and potential energy when the position is 3 cm. So the question is actually very similar to the example we have just seen. So what do you need actually? Right. Just trying to see if I could draw on a whiteboard. Okay. Right. So you have basically question 2. M is equal to 0.05 kg. The K is equal to 35 Newton per meter. 35 Newton per meter. So in the first part, you are asked to calculate the total energy. In the part A, the total energy 1/2 Ka squared. So amplitude is 4 cm, so 0.04 meter. So you could easily work out what is the total energy. Part B, speed of the object when it is at a location 1 cm. So velocity, it is equal to plus or minus. Well, if you are just asked to determine the speed, you could simply write, as your class name suggests, positive value. So it is omega square times square root a square minus x square. X in this case is 1 cm, 0.01 meter. And then in the part C, kinetic energy at the position of 3 cm. So first, you have to decide what is the velocity at x equal to 3 cm. Still, you use the equation omega times a square minus x square. In this case, x is equal to 0.03 meter. And afterwards, you decide what is the KE, 1/2 mv square. And finally, potential energy is just 1/2 kx squared. So I'm just trying to point out the equations to be used. And in this particular example, actually, you could work out the equations quite easily because it is very similar to the example in the lecture notes that we have just seen. Right. So let me see. For the time being, we would take a break around 10 to 15 minutes. It is slightly longer than usual because we would come to the usual practice of having the quiz on the U reply. So you will see it here that we have the U reply quiz again. There are 4 questions, but they are actually 4 parts of the same question. Because of the format, I have to put them into 4 different questions, and they are multiple choice questions actually. So we would take the break for the time being, and please try to complete the questions during the break. Okay, I should give you until 4:35 to finish the questions in the you reply. There are 4 multiple choice questions, and they're actually the same question, just asking different aspects. So hopefully 4:35 should be enough. Okay, we still have here a few students who have not submitted. So please hurry up. We should not be waiting for too much longer. Right. Okay. Right. Last 10 seconds. Okay. Now, we should come back to the lesson. And we will first take a look at the second scenario of the simple harmonic motion before we talk about the significance of the simple harmonic motion. Here, we would be looking at a different type of a simple harmonic motion. Well, to be fair, we should not say whether it is simple harmonic motion or not until we finally decide that it follows the general equation form. It follows the general equation form of A that is proportional to minus X. Only if it follows this equation form, then we could say it is a simple harmonic motion. So the situation on hand is what we call a simple pendulum. We have seen that at least in old days where you have a clock with the pendulum, or even if you have just a string that is tied to a heavy object, it could still be considered as a simple pendulum. So the idea is like this. You let the gravity to do its job by, say, raising the heavy object at an angle from the vertical position. So the vertical position is considered to be the equilibrium position, because if the whole mass is at here, the string and the center of gravity, they are on the same line, there would not be any tendency for the object to move either to the left or to the right. But if you raise the object and you let it go, there would be a tendency for the object to come back to the equilibrium position at the center. So how do we analyze this particular motion? The way to do the analysis is summarized in the free body diagram on the right-hand side. Of course, you have the mass, there is a weight. So this is mg, and as well as the tension. The two forces are not along the same line, so there would be at least a net force in the horizontal direction. But rather than considering the force in the horizontal direction, let us consider the forces in two perpendicular directions. One is along the direction of the string, and one is perpendicular to the direction of the string. So in the language of the physics, it would be the transverse direction and the radial directions, or the tangential direction and the radial direction. In the tangential direction, you have mg sine theta. And in the radial direction, you have the tension of the string as well as mg cosine theta. Ideally, mg cosine theta and t should cancel one another. Otherwise, it would be accelerated along the string direction, either towards the hanging point or away from the hanging point, which does not happen. So they are typically canceling one another. What is left behind, therefore, would be the tangential force, mg sine theta. It is not balanced by anything, so it would really cause the acceleration of the object. So you have the acceleration in the tangential direction, ma, which is equal to minus mg sine theta. So a acceleration, it is equal to d square s over dt square. But here, we could rewrite the acceleration into, well, the longitude, the linear acceleration into angular acceleration. So that is the important point. S is equal to L times theta as long as theta is small. So this is a very important assumption. Theta is small. Then S is basically equal to L theta. And the second order derivative of S with respect to t is equal to L times second order derivative of theta with respect to t. So that is why you have the equation at the top. And the force is minus mg sine theta. And acceleration is ma. Well, the acceleration is d square s over dt square. And it would be also L times d square theta over dt square. Now we compare the two terms, this one and this one. If theta is small, sine theta can be very close to theta. And that is a very important conversion, because once you do it, the equation form becomes this one. So you have the sine theta in the second term, and then it can be considered to be theta if theta is small. Now, here it is the second order derivative of theta with respect to t, basically angular acceleration. Here, it is the angular displacement. So we come back to the equation form, acceleration that is proportional to displacement. Of course, here we are not having the linear acceleration. We have the angular acceleration. D square theta over dt square. And that is proportional to theta. And you see the negative sign. The negative sign comes in because here you have the force which is pointing in the negative direction as the displacement. So that is why the negative sign comes in. So here you have the equation form like that, which is the required equation form for simple harmonic motion. What is the omega square in this case? If you compare the equations at here to this one, you will see that for the simple pendulum, omega square is equal to G over L. For the case of the simple pendulum, omega square would be equal to G over L. So omega is equal to square root G over L, different from the spring mass system. So that is why we have to decide the omega according to the equation of motion that we have established. The equation of motion we have established is d squared theta over dt squared equals to minus G over L times theta. So this one, G over L, is omega squared. And because it fits in the equation form like here, so it is a simple harmonic motion with omega equals to square root G over L. Now, what does this equation tell us? Let's take a look at the next page. What does this equation form tell us? Of course, it tells us that it would perform a simple harmonic motion with the particle displacement or angular displacement that is in a cosine format. Once again, whether it is a sine function or cosine function depends on initial condition. If you release it from the maximum displacement, it would be a cosine function. If you start from the equilibrium point and give it a kick at the equilibrium point, then it is going to be a sine function for the particle displacement. So you have to decide it case by case. The angular frequency, however, is determined by omega. Omega is equal to square root G over L. So the period 2 pi over omega is equal to 2 pi times square root L over G. Now, what is special about this equation? In this equation, you see that the period of the oscillation depends only, if you forget that G is variable, assuming that you are on the Earth's surface and G is constant, then the period depends only on the length of your simple pendulum, the length of the string, if you like. So if you have a very long string, you would expect a very long period of oscillation, just like playing the swing in the playground. If you have a very long chain, the oscillation period will be long. If you have a very short chain, the period of oscillation will be short. So this equation provides the physical explanation of the observation. And it does not depend on how much you displace the particle at the beginning. Now, that is with a very big assumption. That is with a very big assumption that theta is small. As long as theta is small, typically smaller than 10 degrees could be considered as small. If it is small, if the theta is small, then the period is independent of the amplitude of the oscillation. Just like in the quiz that we have just done, the period of the oscillation for the spring and mass system, omega, for the spring and mass system is equal to square root K over M. it is nothing related to the amplitude. It just depends on the inertia and the spring constant. Similarly, at here, the period depends only on the length of the string, and if you like, the acceleration due to gravity. But at the same location on the Earth, g should be constant. So only the length matters. Only the length of the string matters. Okay. So that is the application of the simple harmonic motion, as in the case of the simple pendulum. We derive it by ourselves that the motion is simple harmonic, and the period of the oscillation is determined accordingly. There's a classmate asking how to get G over L. Well, next time, once again, please put it as an open question to all, so everybody could share. It doesn't really matter. Questions you may be shy to ask, but it can be important question to all the classmates. Thank you. How to get G over L? Well, we are not getting G over L. We derive it. We derive it by considering the equation of motion for the particle hanging on a string. So we start from the equation of motion, considering, let me see, considering that here, F equals to ma. So what is the force? It is the restoring force, mg sine theta, with a minus sign because this is the positive s, then mg sine theta points in the negative s direction. So from this, we work all the way to here and obtain omega squared equals to G over L. Okay. Now, in the tutorial, you also have another question that is related to the simple pendulum. I'm not going into the details or go into the question and work it out, because you could try it by yourself and see how to obtain the answers. So I will let you do it at home. And here I will just briefly go through the importance of the simple harmonic oscillation. Well, here an example is given for materials. In the materials, you have a lot of atoms, and the atoms are held together by some kind of a chemical bondings, by some kind of a chemical forces, if you like. And because of the inertia and the spring, so they are acting like the spring and mass system. Therefore, they would be oscillating from time to time about their equilibrium position. So it is of great importance in terms of materials for the simple harmonic motion. They decide many of the behavior. For example, the electrical properties or the optical properties of the materials when they are exposed to different external energy. Or if you go to some other experiences or examples that are more related to our daily lives, and very vivid example would be the one that you could easily find on the internet. So if I just try to find it quickly on the internet, let me try to show you. You would probably have seen it, but it's always good to see it again. This is a very famous example of resonance or oscillation. And it is a real example.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months.
So this is a bridge in the USA. They managed to build it, but because of simple harmonic motion, or actually
During
oscillations.
construction, we see the steel girders, 8 feet tall, which were
Because of the oscillation with special frequencies that matches with the
A professor of engineering went out to see what had happened. He's coming back,
very strong
walking with some difficulty along the nodal line, which is the center stripe of the roadway.
And at the end, of course, disaster happens. This is not computer animation. This is real.
It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this.
So at the end, you would fully expect what would happen. And it is just a disaster caught on the video camera.
The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge.
Okay, so movie over. Basically, the story told. So in, for example, mechanical engineering, which some of you are studying in that department, oscillations is very important. And to be more important, sometimes is to control or to suppress the oscillations. For example, in the large structures like the bridge, how do you suppress the oscillations? That is a very important topic. And you will study in much greater details later. But all of the things start from the simplest case, and that is the simple harmonic motion. Right. I think the discussions on the simple harmonic motion would stop in this way. And we have still some other topics related to the oscillations or the waves that we would discuss. And that comes to the next topic of the sound wave in the lecture notes number 3. So before we talk about that topic, maybe, well, I just happened to be using this computer to show the YouTube video. I will show you a related discussion, actually, that comes up a bit later in the lecture notes. And that is one of the special effects of the waves that is commonly discussed in the sound waves. So that is the Doppler effect. So I will just play it. It is around 7 minutes, I think. Hopefully that would cheer you up after the whole 1.5 hours of lesson.
Named after Christian Doppler, a 19th century mathematician and physicist who was able to mathematically describe what is now called the Doppler effect. And it sounds like this.
Live in physics. 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 Live in physics.
Perhaps you are already familiar with how the Doppler effect sounds. However, I'm here to make sure you understand why it sounds this way.
Oh, great. I always want to know why.
Me too. Actually, you know what? I do too.
All right, so it starts by recalling what this animation of a stationary sound source actually represents. So, Bobby, remind me, please.
Well,
Actually, rather than using the car horn, let's switch to a constant 440 Hz frequency being played on the speakers of the car stereo. That is the 440 Hz concert pitch, which we used last time.
it's harder to hear the Doppler effect at 440 Hertz rather than the car horn. Can we just stick with the car horn?
Okay, we can go back to the car horn. However, the Doppler effect is easier to understand if we refer to a single frequency. So let's keep referring to the demonstration as a single frequency, but use the car horn demonstration. Sorry, Bobby. We're back to you. You are telling us what this animation of a stationary sound source actually represents.
Right. Remember, sound is a longitudinal pressure wave,
And those lines are crests.
which are also called wave fronts.
Yeah, thanks. So sound is periodic changes in pressure in the medium, which in this case is air. Each of those lines represents a crest in the longitudinal pressure wave. That means each crest or wavefront is a location of high pressure. That periodic pressure wave transfers sound energy through the air. And the reason all those circles are the same distance from one another is because the sound source is oscillating in simple harmonic motion at a constant frequency.
Do not forget that each circle actually represents a spherical pressure wave or wavefront going out in all directions from the sound source. It is a circle instead of a sphere here because this is a two-dimensional space.
Very nice, everybody. Now remember, this animation is for a stationary sound source. Look at how the animation changes when the source of the sound is moving.
Huh, I like that.
Good, but I want to make sure that you are aware that each of those circles, which are actually spheres, represent the sound coming from where the sound source was when it emitted the sound. To make that clear, I have highlighted one of the wave crests so you can see that it is a sphere that is increasing in size, and the center of that sphere continues to be in the location where the car was when the sound was emitted by the speakers of the car. Sometimes that is a concept which gets lost in the overall understanding of this.
Okay,
Thanks.
got it.
Okay.
Now let's add a human to our animation. Notice the human, or the observer, is currently located such that the car, the source of the sound, is coming towards the observer. Bo, what do you notice about the distance between the spheres that are going towards the observer?
On the side of the car where the guy is, the circles are closer to one another.
And what does that mean?
Well, the circles represent crests in the wave, and the distance between two crests of a wave is the wavelength of the wave. I guess that means that the wavelength of the sound wave which the guy hears when the car is moving toward him is less than the wavelength of the original sound.
Correct, Bo. The wavelength of the sound heard by the observer when the sound source is moving toward them is smaller than the wavelength of the original sound. And Billy, what does that mean for the frequency of the sound heard by the observer in this example?
Okay, the observed wavelength is decreased, and you are asking how that affects the observed frequency. Well, we know the speed of a wave equals the frequency of a wave times its wavelength. That means the frequency and wavelength of a wave are inversely related. That means if the observed wavelength is decreased, the observed frequency must be increased. In other words, when a sound source is moving towards an observer, the sound heard by the observer has a smaller wavelength and larger frequency. A larger frequency sounds like a higher pitch to us, so the sound we hear when the car is coming towards us has a higher pitch.
Absolutely correct, Billy. Bobby, could you please talk about what happens when the car is moving away from the observer?
Okay, this should be the inverse of what we just talked about. Now the crests are farther away from one another, so the wavelength of the observed wave is larger. Wavelength and frequency are inversely related to one another. So because the observed wavelength is increased, the observed frequency is decreased. That is why the frequency and pitch of the observed sound are lower when the car is moving away from us.
Very nice, Bobby, but I want to specify that the frequency and wavelength of the sound source remain unchanged. To reiterate that point, please enjoy this split screen of two different viewpoints during the demonstration. On the left, you see me in the car, and on the right, you see the event from the perspective of the stationary observer. Before we heard what was happening from the perspective of the stationary observer. Now let's listen to what we hear from inside the car. The frequency and therefore the pitch you hear is constant.
Sure, the person who is in the car is not moving relative to the source of the sound, so the wavelength and frequency they observe are not affected by the motion of the car. Thanks.
But what if it's reversed and the car is stationary and the person is moving?
Great question, Bobby. That actually causes the same Doppler effect. If the sound source is stationary and the observer is moving, as the observer moves toward the stationary sound source, the observed wavelength is still decreased, and therefore the observed frequency is still increased. And the reverse is true as the observer moves away from the stationary sound source. Thank you very much for learning with me today. I enjoyed learning with you.
Okay. It's nice to have somebody doing the teaching for me. Okay. Now, of course, it is actually the topic, the main topic in the chapter 17 of the lecture notes set number 3. So if I go back to the lecture notes, which is here. So actually we have already moved to the chapter 17 of the lecture notes. And the chapter is related to the sound waves, and there's no specific reason why the Doppler effect we have just seen is occurring only in the sound wave, but it is something most observable if it is in the form of a sound wave. In fact, Doppler effect can occur in also the light wave, and that is how people have made very important discoveries of the moving stars. For example, the black holes, the expansion of the universe, etc. They are all discovered by means of the Doppler effect. And in order to understand the Doppler effect, the simplest way is by some experiments that we could do on Earth, and that is by using a sound as a wave and demonstrate the Doppler effect. So firstly, we would try to understand the basic properties of sound waves and the speed of the sound before we actually go to the Doppler effect, which may actually be the topic of the next class. So here we just go through some of the basic properties of the sound wave before we go on. When we talk about the sound wave, typically we are referring to the sound that we could hear. But of course, the sound wave, which are just some oscillations of the air particles, they could exist in different frequencies. And for the human ear, the hearing frequency is in the range between 20 hertz to 20,000 hertz. And there are, of course, sound that exist below this frequency range, and they are referred as the infrasound. And those above the 20,000 hertz would be referred as the ultrasound. They cannot be heard by our human ear, but they are very important as well. For example, the ultrasound, they are used very broadly for medical purpose. They could be used for breaking the stones, for example, in the liver or in the kidney. If you have stones, if you have crystals that are developed, they could be making you very painful. And by means of the ultrasound, you could break them. Or you could use the ultrasound to image the tumor or babies. Of course, we could have sound energy that are very different when you use it for imaging and use it for damaging. So it is just like you are speaking to somebody or you are yelling at somebody. The energy is different. So the same kind of sound can have different effects depending on the energy. But here we try to understand the sound in general, which is the longitudinal wave that exists in air due to the compression and the rarefaction of the air particles. So you have the transmission of the sound wave due to the continuous compression and rarefaction of the air particles. Say at here you have a piston, or more generally, you have a sound source that are oscillating back and forth. When it pushes forward, it will compress the air. So this high density of air particles would generally lead to a high pressure. This high pressure would push forward and keeps pushing to the front and brings to the transmission of the sound energy. When the loudspeaker moves back, it would generate suddenly a low density of air particles, and this is the region of the rarefaction. Basically, the trend of the sound waves is the trend of such compression and rarefaction. So this is the general nature of the periodic sound wave. And a very important property of the sound wave is, of course, the speed of the sound in the air. Now, the speed of the sound in the air depends actually on the temperature as well as the medium, the exact type of gas. Of course, generally, you would have, say, air, which is a combination of nitrogen and oxygen and some rare gases. You have more than, you have around 78% of the air being nitrogen and around 16 or 18% being the oxygen. The rest of them are some other gases, for example, carbon dioxide or some noble gases. So the speed of the sound in air depends on the temperature as well as the composition. In particular, for air, the speed of sound is determined by the equation like this. There are ways to derive it, but that is far beyond the current level of understanding for this course. And actually, if you have a different type of gas, for example, helium gas, which is much, much lighter than air, the speed of the sound would be changed as well. Typically, lighter gas would have a higher speed of the sound. So here is just a quick demonstration, mathematically quick demonstration, how the speed of the sound changes with the temperature. Here, the temperature is in degrees Celsius, and that is why you see the funny number of 273, which you would recognize it is the absolute temperature for 0 degrees Celsius. So this is given it here to you just for your information. And actually the speed of the sound in different media can vary quite a lot. Say the sound, when we refer to the sound, we are typically referring it to the oscillation of the particles in air. But if you consider the oscillation of the particles in other media as sound as well, then the speed of the sound in different media can actually be varying quite significantly, depending on the medium. They are all shown at here, the speed of the sound at 25 degrees C, or room temperature, if you like. Here you have some other temperatures of a gas at 0 degrees C, which should not change a lot compared with the room temperature, but you could still see a great difference. Medium, which are liquid and solid, they generally have a much higher speed of sound compared with the air. One way to understand this is you have a very strong bonding or very strong springs, if you like, that holds the atoms together. So they are much more effective to transmit the energy. So if you understand the sound as a way of energy transmission, then you will see why the speed of sound is higher in the solids, because you have stronger springs, if you like, between the atoms in the solids or in the liquid, compared with the gases. Atoms in the gases, they are actually not held together, but you rely on the pressure difference to push the energy forward. So that is quite a different scenario. Right. So at here, the main topic of a discussion in this chapter is the Doppler effect. Luckily, I found this video in the morning, and so it saved me quite a bit of effort to explain the situation. So there are a few important points highlighted in the video. First is that no matter it is the source or the observer moving, when you have a sound source that is performing a relative motion with an observer, there would be a change in the observed frequency. Notice that he highlighted a very important point. The source itself has never changed. The source frequency has never changed. It is only the observed frequency that is changed. That is a very important message. So for example, if you have a car making a hooting or the siren from the police car, when it is stationary, it plays a certain frequency. To the policeman inside the car, the frequency is still the same. But to the observer outside, whether it is the police car moving to the observer or moving away from the observer, this would have a direct influence on the observed frequency by the observer. So how do we understand such a scenario? Basically, we try to understand the effect by considering what happens when you have the source or the observer moving. So in the video, it explains the situation when the observer is stationary and the source is moving. So why not we just try to go to that one first. In the video, if you remember, they are trying to show you various circles. Those circles represent wave fronts. So they are the, if you like, maximum points of a certain compression wave. And they are forming circles because the sound is emitting equally in all directions, and they are transmitting equally in all directions. After all, it is air, and there is no reason why the speed is higher in one direction compared with the other. So they are going in the form of circles, but at the same time, the source is moving. So to the observer A, the source is moving to him. So the wavelength, apparent wavelength of the sound coming from the source is shorter compared to the case of observer B, where the source is moving away from the observer B. So the apparent wavelength gets longer. The question is, what is the apparent wavelength for observer A and observer B in this case? So here is the equation. The apparent wavelength lambda dash, it should be equal to lambda, which is the wavelength of the sound for a stationary source, minus delta lambda. For the observer A, it is the equation lambda dash, the new wavelength is original wavelength minus delta lambda. This delta lambda comes from the fact that the source is moving. So in between two circles, the time difference is 1 period of oscillation. And the car has moved a distance of Vs times t. So Vs is the source speed. T is the period of oscillation. So this would be the change of the wavelength. So for the observer A, the apparent wavelength is lambda minus delta lambda. And it becomes lambda minus Vs times t. Of course, you could write it as lambda minus Vs over f. Similarly, for the observer B, it becomes lambda plus Vs over f. So the apparent frequency would be the speed of the sound. Let me see if it is the, no, speed of the sound, it is labeled as V over the apparent wavelength. Because to the observer A or observer B, he doesn't know whether the sound source is moving or not. So to him, the apparent frequency is just the speed of the sound divided by the apparent wavelength. That is why we have this equation. So if we go back to the next page, apparent frequency is the speed divided by apparent wavelength. For the source approaching the observer, this would be the equation. You could see the source approaching observer, you would expect an increase of the frequency because Vs is positive. That means this term at the bottom is smaller than the term at top. Therefore, there is an increase in the frequency. On the other hand, if the source is moving away from the observer, then there would be a decrease of the frequency. So this is how we derive the equation for the source moving away or approaching the observer. So the apparent wavelength, yes, it can be changed by our movement. So to the stationary observer, the wavelength could be changed. And actually, your classmate is asking a very good point. If you have the wavelength changed by the source, what will happen? for example, if the source is moving faster than speed of sound. So here we could see that the speed of the sound is v. What happens if Vs is larger than v? It seems that it would come to a negative frequency. And that is not physical. That is not physical. And that would come to actually another topic later in the lecture notes called the shock wave. That is something we will discuss actually in the next lesson. One of the classmates is asking about how to know the magnitude of delta lambda. Well, the magnitude of the delta lambda is decided here. You have circles which are the wavefronts. So what is the distance between two circles? If it is a stationary source, the distance between two circles would just be the wavelength. But if you have the source that is moving, for example, forward, in between two circles, it would have moved a distance of delta lambda. This delta lambda would be the change of the wavelength, and the distance moved would be the source speed times the period of oscillation. So that is, well, hopefully what you're asking about. What about observer and the source approaching each other and move away each other at the same time? That is the thing we would address in the next lesson, okay? Right, so I think I would have to stop at here. It is over time. Before we stop the lesson, classmates may have received the exam timetable. It would be on in the December. I can't remember which day, but all of you would have received a seat number. Please note that the PolyU has already sent you an email in September saying that students in Hong Kong, they would be taking the exam in campus. Students outside Hong Kong, because they cannot come back, we would arrange online invigilated examination. So later next week, we would be sending out information how this is to be arranged. So please be patient. There is no change of such a plan. The plan is still the same as in September. So there's no need for you to send in emails asking why we have to come back, how we will come back, and etc. We just would keep on the same plan. Students in Hong Kong take the exam in campus. Students outside, we would arrange online invigilated examination. I'm sure that that is not something easy, but we have to go through it, okay? So we will stop the lesson at here, and we will carry on next Monday. Okay, thank you.